Hello and welcome to second part of module 5 network design and planning. So in this part of the video we are going to look at the LAN WAN design. Now there are two models which we are going to look at. The hierarchical model, we have briefly seen this module. We are going to slightly elaborate more on that, and the campus design models. So these two models are something which we will be using as a part of our design assignments. So first let's go to the three-tier hierarchical model, or Cisco's three-tier hierarchical model. We have already seen that this model is basically consisting of three layers: the access layer, distribution layer, and the core layer. Now let us look at each of this layer in slightly more detail with regards to what is their function and basically what kind of configurations are done on this layer. So the first is the access layer, also called as the network edge layer. So this is the point where end user devices like the computers, laptops, IP phones, wireless access point, printers, IP based Xerox machines, etc. They basically, the end user devices connect to the network. Now what is the primary function of this layer? The primary function of this layer is to provide network access to the devices and control which devices are allowed to communicate. So if a particular device is not allowed to communicate, which means it is not allowed to connect to the network, so at this point itself the access for that particular device should be denied. There's no point in saying I'll connect it here and then try to implement my security of denying a particular device at the higher layer. So at the access layer itself, some of the basic things are to be implemented. So let us see what are the key features that are implemented at the access layer. The first is the port security. So ensuring only authorized device plugs into the network. So let's take an example. Suppose somebody tries to shift a computer from IT Lab 6 into IT Lab 2. If I have designed it according to the three-tier architecture, and if I have configured the devices, network devices properly with the port security, what will happen is the moment somebody moves this machine from one lab to another lab, the switch in the other lab will not accept it at all. So you will not be able to connect it. So that's the kind of a port security. The second thing is, if there are any VLANs to be made, if there is any logical groupings to be done, then access layer is the right point where you would be doing the VLAN assignments. So the switch at the access layer should be such that it supports VLAN assignment. The next is the power over Ethernet. So there are certain devices like IP phone or maybe IP based CCTV cameras which require power for operation. So the IP phone requires a power for operation. Now there are two types of IP phones you get an external power supply based IP phones where you have an adapter, and the adapter has to be plugged into the normal electrical socket, and only the cable is to be put, the data cable is to be put to the telephone. But there are some devices where they derive the power also from the switch itself. So such type of devices are known as power on Ethernet enabled devices, so PoE devices. Now when you are using this PoE devices, specifically like IP phones or wireless access points or maybe IP based CCTV cameras, then you need to check that your switch, the switch that you are selecting, supports PoE. Second thing, you need to also check what is a wattage of power this particular port is going to deliver, because you don't want a situation where the device is demanding less power but the port is supplying more power, so the device burns off. or the vice versa situation where the device is demanding more power but the PoE port does not seem to deliver that much amount of power. So these are some of the design things which at the time of selection of the switch we need to check. The next is about the quality of service. The device, I mean the network switch at the access layer should be such that quality of service, basically prioritizing of the traffic, should be possible. The reason is because if you are having a voice based systems like VoIP or voice over IP based systems, then you need to do prioritization, especially for the voice that travels over the network. So the switches which you would select for the access layer would essentially support configuring quality of service. The next layer after the access layer is the distribution layer, also known as the aggregator. The distribution layer acts as the boundary between the access and the core layers. So it is basically sitting between these two layers. It aggregates the data from dozens of the access switch before sending it to the core. So there are a lot of switches which are connected to this distribution layer switches. So access layer switches are connected to the distribution layer switch. Now what is a primary function? There are two basic functions which the distribution layer has to perform. Any routing related decisions the distribution layer does. Your policy based or any security implementation that you have to do, security policy implementation that you have to do, that has to be done at the distribution layers. So essentially when you are selecting the switches for the distribution layer, you need to see whether the switches are supporting these two functionalities or not. So just elaborating on those two requirements or two key features. The first is inter-VLAN routing. See, in the access layer we said that we are creating VLANs. But suppose if I want to communicate from VLAN 10 to VLAN 20, then I need to support inter-VLAN, that is from one VLAN to another VLAN routing. Now, in order to do this, the distribution layer routers needs to be configured with inter-VLAN routing. Okay, so they need to have the capability, the switches needs to have the layer 3 routing capability. Okay, or the routers needs to have inter-VLAN routing capability. The next is about security policies, the implementing of ACLs, which is access control list, which means which IP address is allowed an access to, what kind of an access is allowed, what protocols are allowed, whether TCP protocol is allowed or UDP protocol based access also can be done. IP based access can be done, user based access can be done. So there are different types of ACLs that can be configured onto this network devices. This helps to filter the traffic from getting into the core. Like for example, if I want the student VLAN should not be able to access the faculty VLAN, but faculty VLAN should be able to access the student VLAN. That kind of a configuration or security policy implementation can be done on the distribution layer. Then another important aspect of the distribution layer is redundancy. So providing redundant path back to the core so that if one link fails, the traffic is seamlessly rerouted. So any kind of a link redundancy, generally at the distribution layer we would do link redundancy because the device redundancy might become a slightly costly affair. So device redundancy normally we would do it at the core layer, but link redundancy we would do it at the distribution layer. Coming to the core layer, which is also known as the backbone of the network. The core layer sits at the top of the hierarchy. It connects all the distribution layer devices together. Now, what is the primary function of this core layer? To switch traffic as fast as possible. So therefore, the routing tables or the switching tables at the core layer should be minimum. Okay, you don't want to have a very extended switching table because the lookup time will increase. The core should not be burdened with complex routing policies, security filters, or endpoint connections. So you don't want too many of the security policies. So security is basically a role of a distribution layer and not of a core layer. So what are the features of the core layer? High speed switching. It should be able to do a very high speed switching. Generally the connectivity at this layer is fiber optic, because that provides a high speed data communication. The second important thing is it should be designed for high availability. That is, if a core of a network fails, then the entire network fails. So you don't want the core of the network failing, and therefore here you will have a device level redundancy, which means if I am having one switch, I'll be that is, I require one switch in the network, I'll be actually having two switches, and which can be a hot swappable switch or a hot switch, which means the switch is actually powered on and configured. So if something goes wrong with switch 1, there will be an automatic protocol which will detect, and automatically the next switch will come active. And typically in high-end switches, this transition time could be few milliseconds to few, maybe 1 or 2 seconds, not more than that. Okay, so the end user literally does not detect failure of a network. That's what we mean by high availability. And in networking terms, high availability is 5 nines. That is 99.999% availability, which means unscheduled downtime, that is unscheduled failure of a network, should not be more than 5 minutes in a year. So the network has to be up always, and if it fails because of some reason, then that total duration of failure within 1 year should not exceed more than 5 minutes. The next model that we have is a campus network design. So the 3-tier architecture is good when you're looking at an enterprise kind of a network, which is a very large network. But let's say if we are looking at a campus kind of a setup of our institution. So in that case, we do not have a very large campus as a per se, but a fairly medium-sized campus, fairly small-sized campus, small to medium-sized campus. So in such case, having a 3-tier architecture could actually be an overkill. So you don't want too much of bureaucratic architecture. One reason is because if you have too many devices put together, then there's a cost which gets involved into it. So let's just understand what this campus network design is. A campus network is essentially a large LAN that spans multiple interconnected buildings within a specific geographic area, such as a university or maybe a corporate headquarters or a small industrial park. Okay, so in such case, a collapsed core architecture is used. This is nothing but a 2-tier model. We'll see what is this 2-tier model, which is basically a modification of a 3-tier model. So how does this work? Is you're having a 3-tier model, that is access, distribution, and core. Now, instead of creating this distribution and core separately, because that adds to the cost, but at the same time it gives me same network efficiency and same network performance. So there's no point in having two different layers of distribution and core, and I merge them together. Okay, and this is called as a collapsed core. So the distribution, the functionality of distribution and core layer is mixed. Now what happens because of this is the security policy and routing decision were the primary features of distribution layer, which now have to be taken care by the core layer. So this slows down a core to a certain extent. But since the campus is small, the data traffic is going to be very limited, so it really does not affect the network performance, and therefore the collapsed core can work. But for a large organization, you have to go for a 3-tier network. For a small organization, for a small campus with maybe 4 or 5 buildings, which are like 5 to 6 floors, a sizable amount of small size of organization, this collapsed core architecture can be sufficient enough, which can be decently cost saving, but at the same time give you a similar amount of performance. So the functionality of the access layer remains the same even in the collapsed core architecture, and the distribution layer and the core layer functionality which was there in the 3 tier will now have to be managed by the core layer itself. Yeah, so that's it. Thank you very much.